So this is CPM Calculus Chapter 3, number 78. The position of a ball as a function of time is given by the function below, where S of t is in meters and t is in seconds. Okay, so S of t is defined to be the square root of t plus 1. Use your calculator to approximate the instantaneous velocity of the ball at 1, 5, 10, and 100 seconds. Okay, so remember what we need to know is the instantaneous velocity given a graph that is distance and time, right? We know velocity is change in distance over change in time. Velocity is change in distance over change in time, which is the slope, right? The slope, here is our y value, here is our x value, change in y over change in x, so this is the same as the slope. Okay, so let's go ahead and use our calculator, it says right there, to approximate it at time 1, 5, 10, and 100 seconds. Okay, so here's my calculator. I'm going to go ahead and go straight to graph, and I'm going to plug in square root of x plus 1, right? That's the function. Even though it's t, I'm using x plus 1, okay, because my calculator uses x and y, right, in this mode. So let's just graph this and see what it is, right? It should go like this. There we go. So this is our square root of x plus 1. So at time 1 second. Okay, so we can use our calculator to find this really easily. Remember, math, F5 to go to math. If we go down to the tangent line, right, it will draw the tangent line at specific points. So we could go ahead and say the tangent at, well, we want it at 1, right? Well, tangent at 1, so it's going to draw this line. That's the tangent line at x equals 1. It's also going to give us the equation. Y equals, so this is a TI-89, y equals 0.353553x plus 1 whatever, right? So it's in the form of y equals mx plus b. So the slope for the tangent line at that point is 0.353553x, or sorry, no x, 0.353553. So that means at time is 1 second, right? Our velocity at 1 second is approximately 0.353553 meters per second, right? That's the slope at that point. Okay, so we can go ahead and use using F5 to go to math. We can keep doing that and getting the tangent line and looking at the slope. Well, if you also look here, another feature our calculators have is number 6 is derivatives. So we can actually ask it, what is the derivative? So let's do that for 5. The derivative dy dx at x is 5. So I typed in 5, and it's telling me right there, well, that is the slope. That is the derivative at x equals 5. So at t is equal to 5 seconds, right, the velocity at 5 seconds is approximately 0.204124 meters per second, right? So let me go home and graph really quickly. Well, let's go back here because I want to get rid of the tangent line. Okay, so if I graph it again, the tangent line is gone, right? I want to just show you that you don't always need to see the tangent line. Okay, so let's go ahead and get it at 10 seconds. So I'm going to F5, derivatives, dy dx, and now I want to see dy dx is the slope function, f prime of x. It's just another way of saying it, at x is 10 now. So it's going to go over to where x is 10. It's going to tell me exactly what the slope is there, or the slope function at x is 10. So at t is equal to 10 seconds, our velocity at 10 seconds is approximately 0.150756 meters per second. Okay, so 1, 5, 10, and 100 seconds. So let's go ahead and do at t is 100 seconds. What is the velocity? Approximately. Okay. So here, let me just zoom in my calculator. Let's zoom in a little bit so I could show you exactly how to do this. So F5, go down to number 6, right? That arrow means go to the right, and we want to choose number 1. So I want to enter. So I can move this down here and enter, right? So then it says dy dx at. So that's saying f prime of x, or the slope function, at what value of x. So now I want to go ahead and put in x is 100. So I go down here and I put 1, 0, 0, enter. Oops. And that is right now outside of my window. So what do I need to do? I need to change my window first. So let's go ahead and use zoom, and let's zoom out. Okay, I could do that. Zoom out, because basically the window is not showing. The window right now is not showing 100, so it can't calculate things way outside of our window. Okay, so let me just go to window and set it to be 100 or around 100. So use the green diamond window, right? X min, X max. So I want it to be around 100. So let me put in, for the minimum X value, let me put 99, right? And the max, let me put in 110. Okay, so that's going to make the domain go from 99 to 110 on my window, right? And the y scale, well, I know the square root of 100 is around 10, or it is 10. So if we have 100 as our t, it's going to be around 10 point something. So let me go ahead and change the y scale to go from, let's say, 0 to 15. Okay, just so we can make sure we're going to see it in our window. Okay, so now let me graph this again. So remember, this is going from x is 99 to 110, and the y value right here is going from, I already forgot, it was like 9 to 15 or something. Let me check really quickly. 15, 0 to 15. Okay. Okay. So now I want to go back here and use my calculator to get the derivative, right? So let me enter there. Derivative at 100. So let me write in 100, right? Enter. And now it will tell me it is 0.049752 meters per second. Okay? So that is approximately the answer. I used my calculator. Great. So I've done all that. Let's go to part B. What do you predict happens to the velocity of the ball after a very long time? So as t grows and approaches infinity. Well, t is 1 second, the velocity is 0.35 something. As t is growing here, the velocity goes from 0.35 to 0.2 to 0.1 to 0.0497. So my prediction, I don't know if this is the same as your prediction, but it seems like as t is increasing, as t is approaching infinity, right? What's happening? Well, v, our velocity, is approaching, getting smaller and smaller and smaller, approaching 0. Okay? So that's my prediction. If you have a different prediction and you have a good explanation, well, maybe that is okay, because we're just kind of predicting. It's kind of like our educated guess. If you have no idea, then you should go ahead and look at the data, right? Because our prediction should be probably 0. Maybe you might think it will get, like, go negative, maybe. Anyway, you might have a different prediction. Okay, so what happens to the position of the ball after a very long time? Well, remember, the position function was s of t. And so the limit as t approaches infinity, well, the limit as t approaches infinity of s of t, well, that's just equal to the limit as t approaches infinity of t plus 1, right? That was our function. Well, as we get bigger and bigger and bigger, the square root is going to grow, right? And as we approach infinity, the square root of infinity is still approaching infinity. So this is still approaching infinity, right? We don't like to say equals infinity. We know that infinity does not exist, right? But still, what happens to the position of the ball, right? The position, let's call that S of t, right? Well, let's just call it S. S is approaching infinity, right? That's going to be my answer. So does this make sense given to your answer in part B? Well, not really, right? Because if my distance keeps growing, right, my distance is getting bigger and bigger and bigger and bigger and bigger, but my velocity is getting smaller and smaller to 0. If my ball stops moving, right, how does my distance keep growing? So, does it make sense? Not really right away. But if you look at, remember when we graphed it on the calculator, right? The function square root of x plus 1, right? It starts here at -1 and goes to the right, right? Like this. Well, as you notice, it grows really fast here, but as x gets bigger and bigger and bigger, right, it's still growing, but it's growing slower and slower and slower and slower and slower and slower, right? It keeps going, it's still going up. There's no asymptote preventing it from going up, like so there's no horizontal asymptote. So it's still getting bigger and bigger. So our distance, right, is still going up. S is still going up. But velocity, right, the slope, if you look at the slope, well, it's steeper here, steeper. Well, the slope is approaching 0, right? The bigger and bigger we get here, we're still going up. But as we're approaching t or x here, as we're going all the way as x goes to infinity, right? S goes up, yes, but our slope becomes 0, right? And our slope is what we see as our velocity is just our slope, right? Because it's our distance over time graph. All right, so these numbers don't make sense right away, right? Does it make sense? Not right away, but when we think about it, yes, it works out, okay? And you should think about it, and it should kind of make you think like, I don't understand why the velocity becomes 0, but our distance keeps growing, right? But then if you look at the graph and you notice that it's growing still, our distance growing, but it's growing slower and slower and slower, and ultimately it's so slow that you can't even tell that it's growing, but it still is growing, right? Our distance is growing, we're getting further, the ball is going further. But the slope, the rate that it's moving, it seems like it's not moving at all. All right. Okay, so this is the end of CPM Calculus Chapter 3, number 78.